Excellent. So in today's lecture, we're going to cover the final subsection of chapter 4. That's going to be floating point numbers. So up until now, we've talked in depth on how our systems are able to go ahead and store and process integer data in both unsigned and signed formats. So now it's time for us to start considering how do our systems start processing numerical data as real number types. So let's slowly go through the concepts that is going to drive this subsection. And if, for those of you who are online, if you have any issues hearing me, please let me know. Okay, so our floating point representation, as we're going to see in this section, is going to be encoded in the mathematical form of V. V is going to represent our floating point number, our bit vector, and we can represent that giving some x times some power of 2, where the power of 2 is y. And so we'll see the breakdown of that is V represents our floating point number, X is going to be the mantissa or the significand, and then the Y is clearly the exponent by which we're going to raise the power of 2 for. So we're going to break that down. We're going to show samples of that, but that's the general mathematical form we're going to take. So why do we want to model our formula like this? And we're going to see this in subsection 2 of this slide deck, but it's because it's going to be really useful for being able to encode very large numbers. And it's also going to be very useful for being able to encode numbers that are very close to 0, which are also very large in terms of creating a binary string. So again, right here is really the motivations on what we're going to learn throughout the course of this. We'll go into much more detail as to how we're able to capture this with the IEEE floating point standard, which is going to be how we represent our numbers and how we're going to process our real numbers. We're going to also, now that we're starting to talk about real numbers, we have to understand that inherently, mathematically, by definition, they are approximations. And so because of that, there's only a finite sequence of numbers that you can actually sort of represent any kind of partial value, any kind of fractional value. And so you will have rounding considerations. And so you'll have different rounding considerations, even depending on the base of your number. We'll look at that again when we get to the subsection like 4, I think, or 5, when we start talking about how to round or rounding considerations for real numbers. We'll look at the mathematical properties, just like we did with the integer numbers. We'll look at how to add floating points, and we'll look at how to multiply, and some of the consequences about trying to use a relational operator, not an equality operator. You're going to use relational operators on your floating point numbers. Excellent. Okay, so the next thing I want to do is I want to define our radix point. So probably the term many of you use for the floating point that you put between your numerical values to represent a fractional component to it is a decimal number, but that a decimal point, but you only use that if it's base 10, right? Clearly. So here we're going to call this a binary point. The generic term for this is the radix point. So our binary point is going to be the same symbol we use when it's applied to our decimal numbers. And the concept is going to be the same. Any numerical values that are to the left of our binary point will be a non-negative power of 2. So it's going to be a non-fractional. It's going to be the exponential value of our number, and any bits to the right of our binary point are going to be a negative power of 2, or in the form of 2 to the power of minus I, where I is whatever value inside of our bit string or what our numerical string that we're evaluating. So if we take a look at this example here, where our traditional view of our bit vector, right, starts with the least significant bit. So the least significant bit in the way that we were counting with integers started at 0. So if I had my binary point, the first numerical value that's to the left would be my least significant bit, right? And then as I grow out towards I, that's creating a more positive or a larger magnitude of value. And as I increment across the right side of my binary point, I'm going to get a smaller and smaller value. So the biggest of my fractional numbers, just like with decimal numbers, is going to be the one that's immediately to the right of the binary point. And as we get further from the binary point, we're getting incrementally smaller and smaller until infinitesimally smaller by an order of a power of 2. So we can kind of see, and let me move to the next slide.
So you said before the left side is the least significant, right?
So the left side, the very first bit on the left side would be classically that least significant bit that we've been talking about. So that's the bit that would encode to either a 0 or 1. And then the next one, this B1, would be a bit that then could encode to be a 2 or a 3, depending on the state of the bit 0. And then bit 2 would then allow you to encode anywhere between 0 to 7, right? And so as we keep prefixing bits, we keep increasing the magnitude of the number that we can encode in terms of the non-fractional portion. And so once we go onto the right side, where you can see B sub -1, B sub -2, B sub -3, all the way to B sub -j, that's going to represent kind of equivocally what you would think of with your decimal points, where this, for decimal mathematics, this would be like a 10th, right? If you had a 1, or a 9th, if it was a 9 there. Here, it can have a value of 0 or 1. It's going to represent 2 to the power of -1, whereas this would be 2 to the power of -2, whereas this is 2 to the power of -3. In fact, any one of these sub-indices you see here is the exponential power at 2. So this 0 index is the same as saying this is the place where it's 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, all the way to 2 to the power of I. Here, this is 2 to the power of -1, 2 to the power of -2, 2 to the power of -3, all the way until you get to 2 to the power of -j. And so you can see in the red on this chart that we're looking at what it actually resolves to. So like, for instance, in this B sub 0, that could resolve to up to a value of 1. And B sub 1, it could be up to 2. And B sub 2 can be up to 4, right? Now, looking backwards, if we're looking at 2 to the power of -1, another way of expressing that is by saying 1 over the power of 2 to the power of 1, or 2 to the power of 2, right? We put the exponential term in the denominator, which means that the denominator is growing as we increase the power, which means that the number's infinitesimally getting smaller and smaller. So that means we would have a half and a quarter and an eighth, all the way until you have however many bits to encode that fractional value for X amount of precision points.
I have one more question. So I know the left side is significant, but
well, so what I meant by least significant, it's this right here. B sub 0 is your least significant bit for your magnitude, and that means B sub I is your most significant bit in terms of your magnitude. And then we start growing out in this regard. We're going to see what this actually looks like moving to the right side. So you're going to see the concept of least significant bit is going to deviate when we actually start to encode this. I'm just comparing this to what was traditionally the least significant bit up until we're starting to talk about floating point numbers. But actually to encode a floating point number as a binary string is going to be subdivided to 3 different parts. And so then that concept of least significant bits to most significant bits is going to be a little bit different, but we could think of at least the magnitude portion as being the same as like an unsigned number of sorts.
Can it also be like the most significant bit for the right side? The most?
Well, so let's answer that question once we see how the encoding works. Because recall that what's really driving the concept of most significant bit versus least significant bit is the endpoints of your binary string, right? And so here, the only reason why I mentioned least significant point up to this point was to show you how the counting worked in terms of the decimal place, like where the magnitude of our values, our non-fractional portion of our values are going to reside versus where the fractional portion is going to reside. I'm trying to compare it as you would already be familiar with decimal points to show that the motivating concept with binary points is the same. Okay, so to give you an actual example so that we can cut our teeth into this, we have right here some a value of a binary value that uses this binary point. So 101.11, which if I wanted to express this, now previously when we were looking at how to translate our binary sequences into our decimal values, into a base 10 value, we saw that we can simply take whatever the actualization in the binary string was and multiplying it at that place as the exponential of a power of 2, right? So if I have 101, right, I'm going to grab that to the first bit to the left, and that's going to be another way of expressing that would be 1 times 2 to the power of 0, and this is a summation. So then 0 times 2 to the power of 1 plus 1 times 2 to the power of 2. So clearly this portion, in the way that we can translate our binary real number, is no different than what we were doing to work on integers. Now where it deviates is part of this string. Now we can look at those decimal place, we can look at all the bits that fall on the right side of the binary point. And so that now we start decrementing our index, and we use the index as our exponential term as our power of 2. So here we have this one here is going to get multiplied to 2 to the power of minus 1. And then here we have another term after that. So then we're going to multiply that by 2 to the power of minus 2. Now, if I had more terms like a 0 and 1 and 1, I'd continually expand that until I captured where all the ones places were in my binary string, right? And so if I then resolve these exponents and start and resolve these products, I could see that's going to be the same as saying 4 plus 0 plus 1 plus 1/2 plus 1/4. So doing the non-fractional components, we can see we have using a mixed fraction, right? We're going to express this as a mixed fraction, which means we'll have some whole value and some fractional value, or some integer value and some fractional value. The integer value is the same that we would get using our integer operations, our integer arithmetic, but we're going to see that we continually do the summation. And of course, if you want to compute this fraction, you have to get your denominators to be normalized. So that means we're going to have 2 over 4 plus 1 over 4, which resolves to be 3 over 4. So the final value would then be 5 3/4. And so that's how we can translate our binary real numbers into decimal real numbers. Okay, so so you could see the behavior we have is not dissimilar to how we learned we can shortcut doing multiplication and division using shifting operations. Every time we take our binary real number and we shift our binary point to the left, it has the effect of dividing that binary value by a power of 2. And every time we shift that binary point to the right, it has the effect of multiplying that binary value by a power of 2. And we can actually prove that. I mean, you can already see how the binary cells are in multiplicative properties of 2, but let's take that same value we had before in the last slide, this one right here, which was 5 3/4. And let's just shift the binary point over to the left. So by shifting it over to the left, it's going to push all of our values. So one of our values that was on the left side will now move to the right side. And I'll have less values on the left side, which makes up the magnitude of my value, the integer component of my value. So we can see if we then resolve our expression and add it together the way we just saw, instead of being 4 plus whatever it was, it's now going to be 2 plus 0 plus a quarter, a half plus a quarter plus an eighth. So if I resolve that, we could see it's going to be 2 7/8, which is half of 5 3/4. And very similarly, if we push it, we can prove mathematically that using the same technique to expand our binary string or translate our binary string into a decimal representation, that'll be 11 1/2. So you can very easily check and see that you can easily use shifts left and right to do the same thing you would use on real numbers as you would for your integer numbers. Okay, and here is just a quick table just to illustrate this multiplicative property. So we have our binary representation with our binary string growing towards the right direction, the right side. And as we keep appending values, that number is getting infinitesimal, it's getting smaller and smaller. So like we can say that we can have, well, this is a representation of 0, but this would be 1/4 as an example, 2/8, all the way until, so the key that you should see is the denominator of what our fractional number is based off of how many bits we go back. So if there's only 1 bit to the right of our binary point, our denominator will be 2. If there's 2 bits, it'll be 4, right? If it's 3 bits, it'll be 8. So effectively, the denominator is 2 to the power of n, where n is the number of bits that are to the right of your binary point. And of course, we should always highlight that fractional values are inherently approximations. It means they're in some way they're natively lossy, or they're inexact is probably the better term to use there. So, and this isn't just something that's true for computers. This isn't just something true for binary fractional numbers. Any fractional number is the case. And we'll prove this point. There's no exact finite representation in decimal math for 1/3, right? We express that by having to have a repeated value indefinitely. And so we just chalk that up as saying that is how we have to represent that in a base 10 system. So very similar, we can't represent in a very exact way 0.2, because that breaks into fifths, which is not a power of 2. So with decimal math, it has to be able to be divisible across 10 units for you to be able to effectively get a finite sequence to represent with exactness that fractional number. And that's not guaranteed for every possible partitioning. Well, the same is with base 2. So what's interesting, though, is sometimes you can have an exact representation in base 10, like in the instance 0.2. But if I try to translate that into a binary fractional number, all of a sudden I can't represent that. I cannot use a finite number of bits to represent that. It's an approximation. I'll use up as many bits as possible, and then I'll just have to round it off. Now, if I retranslate that value back into a decimal number, I could actually get back a different value. This is why floating point numbers are in particularly kind of dangerous to work with. They're already lossy. They're already instances where you try to capture a behavior and there's only a finite number of memory that you can store. So when you fill it up, you kind of just truncate whatever you're at, and that's now your representation of that number. But then in our computer systems, we are usually doing computations in a base 10 system. We convert it into a base 2 system, then we reparse it into a base 10 system, and you can get a different value out of the system than what you put in. And if you ever wonder why that's the case, that's why. Because it's changing the base can actually have the effect of what was a kind of exact representation into an inexact representation. You lose some values there, you retranslate it back, and now it's a different value.
And that's not even accounting for the different ways that C versus Rust.
Oh, yeah.
Python might try to compensate.
That's right. Because all these decisions on rounding and is it's completely, especially like just an easy way that we'll look at that in class is just the precision points that you have, whether we're using 32-bit versus 64-bit. But this is also should impress upon you why you should always use double the precision, double types as opposed to float types.
This might be outside the scope, and I've never thought to look into this. Does ARM, like the ARM processors versus RISC versus x86 processors, do they handle it?
So that's a good question. That is a little bit out of the scope of this class, but I will say that there are some Intel processors that actually have extended precision beyond even 64-bit encoding. And so they actually go up to an 80-bit encoding for some Intel processors, which can give you an even better representation. Now, when we get into the IEEE floating point standard, one nice thing about that is they've kind of provided a set of rules that's supposed to give us some portability with the expectations of how our floating point numbers are handled. That's right. Yep. That's the important concept behind what drives engineering. Is the understanding that you create measures that become standards that everyone abides by. And that increases expectability, your ability to be accurate and expect certain conditions and constraints to be met. Yeah, hopefully. Doesn't always work. And then there's that famous XKCD comic about a growing number of standards. It's like, these standards suck. Let's make another one. And then all you've done is add another one into the bin. Okay, let's see. So we've already kind of talked about limitations, and this is just impressing upon the concept that a limitation of our fractional binary values is that they're going to be approximations. And so if we wanted to actually see some representations of a value like a third or a fifth or a tenth, these representations would actually create an infinite sequence of bits to try to capture that. So you could kind of see what that would look like until we decide to kind of clip it at some point. Okay, so all of that has brought us to the next subsection in part 4 here, where we're going to start talking about the IEEE floating point representation. What we were looking at before is not how we actually encode our numbers, it's how mathematically we operate on binary digits. So we call that positional notation. We call it positional notation because that's actually how your bits grow out the same way they would if they were decimal values. It's the way that you would do your long multiplication or your long division or your addition or subtraction, just the way you would format it to do basic arithmetic. Now, there's severe limitations with using positional notation if we want to store floating point numbers or our real numbers into our system. And that's because they're not super efficient. You need every one of the bit placements represents a particular value, right? Like the value before, if it were decimal math, you'd have like your tens place and your hundreds place and your thousands place, right? That's what positional notation means when it's a power of 10. Well, in binary, it's the same concept, right? This is my, man, we don't really have a good name for those, right? My truths. It's my power of 0 place, my power of 1 place, my power of 2, but all based off of my value of 2. Yeah. So the idea, though, is if I want to represent a really big number, let's say I wanted to take 5 and multiply it by 2 to the power of 100, valid number and one that I might need to use. If I wanted to encode that as a binary string, well, in positional notation, that 101 that represents the 5, and then I would left shift that with 100 zeros behind it. With positional notation, I'd have to have that many bits to encode that value. And that's just for the really large value. That doesn't have anything to do with the fractional number. Now, like I said, if we want very small numbers, we're actually growing the amount of our bit string in the reverse direction, right? Because in order to capture something very small, something very close to 0, we're infinitesimally having to move to the as far on the right end as possible, which also consumes a lot of bits, a lot of units to be able to capture. So this doesn't scale. It's very impractical for numbers that are very small or for very large. And so the solution here is what we're going to learn on how we actually encode our floating point values using the IEEE floating point. And so the concept that's going to drive, and we're going to have a visualization that we're going to see in just a moment, is that we can kind of break our real number in one of 3 pieces of basic information: a sign bit, an exponent field, and a fractional field. So let's actually see what that looks like. So again, I'm going to give the mathematical form of how we can define our floating point value. So V represents the floating point value as we were looking at it in the last subsection, using the positional notation, using a traditional notation. So imagine V represents our binary point value. So with that said, I can express any positional notation value by effectively using a concept that's similar to scientific notation. Scientific notation where we're actually using a power of 2 to go ahead and encode. So we can see we're going to have our sign bit, which is going to be just here, S, which is going to be an exponent to the value of -1. So if s is 0, then that makes that term become 1 because anything to the power of 0 is 1, right? And if s is 1, then anything to the power of 1 is itself. It's like a self-identity. So that would be -1. So notice that sign bit allows us to make our real number either positive or negative. So this gives us the ability to sign it and not just stay in an unsigned domain. The next one is going to be what we're going to call our significand or our mantissa. And we're going to take a look at this on how we can actually encode this in a moment. So this is going to be our fractional binary number ranged between 1 inclusive and 2. And then we're going to multiply that to some amount of power that is our exponent e. So 2 is our basis, right? We're in a base 2 system. So we're going to have to shift based off of a 2-unit number set. But then our weight on that is going to be represented by e. Okay, so let's look at how that actually gets encoded the same way we would encode our binary strings. So you can see our most significant bit inside of however large our binary word, however big our binary word is, right? The most significant bit is going to be that sign bit. And then we're going to have some amount of our addressable space, our bit sequence, represent our exponent field. But notice it's going to be a smaller amount of bits than our fractional field, which is going to encode our mantissa. Again, so if I were to take this formula, the values that each one of these can have will map into this bit string or this bit vector. Okay, so if this were single precision, I know for a fact 23 of my bits would go into my fractional field. 8 bits would encode my exponent field, and of course the 1 bit for my sign bit. And if it's 64 bits, I get 52 bits for my fractional field, 11 bits for my exponent field, and the 1 sign bit. And this is, again, should indicate to you how much more precision we get with doubles versus with our single precision, which I think we actually, at the tail end of this, in like the appendix section of this, we actually have the highest and lowest values and whatnot. Okay, so with our floating point representations, there are 3 different cases by which our values can be represented. We have normalized values, denormalized values, and we have these special values that are either going to be infinities or not a numbers, not our nads. So let's take a look at each of these cases. The first case, our normalized values that we can encode are the most common that we deal with. So most values fall into this domain. And so really, the condition to be considered a normalized value is that our exponent field is not all zeros or all ones. If it's all zeros or all ones, it's going to be either case 2 or case 3. So provided we have a varying sequence of bits, we can represent some like non-unusual case of a floating point number. Okay, so again, we have in this instance the e in our equation, which I should have put here, will represent the exponent. Yeah, and so did I show? I don't think, did I show how we have to apply a bias? So one thing, when we encode our values, and was that this next slide? So when we encode our values, we have to include a bias term on it. This bias term is applied to our exponent field, and it allows us to buffer up our exponent field so that we can represent our values either as negative or positive values. And we'll actually take a quick look at this. This is an example. I think looking at examples to see how we can translate from a basic decimal number into one of these floating point numbers really helps you kind of grok what's happening and understand. So let's walk through this for a moment. And I have some important formulas to the left. So this is going to be our normalized value for encoding some example. In this instance, the example number we're going to start with is 1,000. I'm sorry, 1,000. It's 15,213.0. Okay, so before we do anything in terms of translating this, let me just make some notes about what these formulas are so that you can understand as I walk through this how I'm doing this translation, how I'm doing this conversion. So the first formula here is the one that we posited to begin with, right? The V represents my bit vector, right? So it's my binary sequence that I have that can have a binary point in it. That's the same as saying, oh, I can have -1 to the power of S, which is my sign bit, times my mantissa number, times 2 to the power of E, which is my exponent. Okay, so with that said, I can also define my mantissa. And so this isn't a mathematical formula. I'm using the C right shift to illustrate how I can take my vector, my bit vector, I can shift it by E number of spaces, and that's going to produce my M. And so my E value is going to be what's encoded inside of my exponent field minus my bias. And my bias is a constant value that is going to, we're going to look at what this is. It depends on whether it's a 32-bit or 64-bit in terms of what its value is. So in this instance, this is a 32-bit. So my value is going to be 127, which is, you know, it's based up to, it's 8 bits, right? So it's effectively going to be an 8-bit value. A max value is going to be what, 255. So my bias is going to be 2 to the power of n minus 1, right? So it's going to be 128 minus 1. So my bias value, and so your bias is a constant based off of the size of what your original word size is. I'll talk about that more as I kind of translate. I'm just kind of giving you information, and then I'll call back to it as we walk through so that you don't get lost with the numbers here. Okay, so we have 15,213. That's in base 10. The first thing I'm going to do is just translate that into a binary sequence. Okay, so now the next thing I'm going to do is I need to go ahead and insert my decimal, my binary place, my binary point, so that I only have one leading number. So is everyone kind of familiar with scientific notation? So this is kind of a similar concept to scientific notation. I'm going to try to get one value at my, to the left of my floating point number, because I don't want to encode too many values there. I have way more encoding space on the fractional field that I have. So I count how many places do I have to shift in order to get my floating point number. So I only have one bit that's to the right of that. If I count that up, it's going to be 13. So now that means my E value here, so looking at this original equation, my E value is going to be 2 to the power of 13. So now whenever I see E, I can think 13, because that's how many units I had to shift in order to get my original binary string into this format. And so these are equivalent to each other. I can say this binary string is equal to 1 point whatever, right? 110, 1101, blah, 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 times 2 to the power of 13. Okay, so now that I've done that, let's define M. Well, M, notice, is once we've shifted to be able to get all of the what was on the left side is now on the right side. Well, that's going to represent my my mantisa, and so I'm going to record that. Now, recall that when we looked at the size, let's go back to this slide. This is in my fractional component, I can hold up to 23 bits on a 32-bit fractional number. So that means that if my mantisa, the amount of units, I only shifted by 13, right? So I have to then append zeros so that it actually fits. So like when you were asking about least significant bits earlier, we have to pad out to make sure that the values that are closest to the binary point are in line. So notice that's going to be the difference, the distinction between my fractional field and my actual mathematical value of M.
On the fraction, are you always going to pad it with, so it's 24 minus 2 to the 14th or whatever your original value is?
Yeah, you'll pad it for as many units that you don't have to fill that word size. And of course, if you're too big to fill that word size, you truncate so it fits that word size. So you either lose data or you effectively are just like adding zero. So equivalently, if this were decimal math, this would be the same as saying one, like if you had 1.25, but you had to fill for 6 decimal places, it'd be like 1.250000, right? Until you get to the amount of decimal places you want. So that equivalently, that's what we're doing. Okay, so that's how we define our significand. So let's look at our exponent value. Well, we already said that it's 13, but in order to actually encode that value into my exponent field, I have to go ahead and add the exponent value to whatever the bias term is. And the bias term is based off of the word size of our floating point number. So this is a 32-bit value, right? And so the actual amount of encodable space that I have, we can see, let's go back, inside of here is 8 bits. And so what's the max value you can have for 8 bits? That's right, there's 256 encodable digits for 2 to the power of 8. And so here, our bias term is defined by being 2 to the power of n minus 1 minus 1. So if it's 8 bits, so then we would do 7 bits, which would be n minus 1. So 7, we would get 128. We subtract 1, that's 127. So every term that we have our E, we would add our bias. So in this case, it'd be 13 plus 127, and that would give me 140, which is represented just like so, as this binary string here. So my frac value comes from this math here. My exponent field comes from this computation of E, our E term, plus the bias, which is based off of the word size that we have for our exponent field. And then finally, our sign bit. And our sign bit, since this is a positive value, would be 0. So does this make sense about how we can convert our decimal numbers into a floating point encoding? And the beautiful thing about this is, since this mechanism is designed around the same way we kind of encode scientific notation, I can do small numbers or large numbers, right? because I'm toggling this value based off of the power of 2, which can, I can encode negative values there as well.
An amazing.
Yeah, it's a very clever solution. Okay, let's talk about some of the other cases though. So we said the normalized case. So let's talk about the denormalized values. So that's going to be our case 2. Our denormalized case is going to be these instances where our exponent field is all zeros. And so when that's the case, that's how we're going to be able to represent our numeric value of 0. Or because if all of our fractional values are 0, and if our exponent field is 0, then that's a 0. Like what we would expect it to be. But if we have all zeros and then our fractional field has some combination of zeros and ones in it, then it's going to be a number that's very close to 0. So that's how we can start encoding our very small, precise numbers, like the ones that are reaching or approaching towards 0. Exactly. I mean, one of the strange things about floating point numbers is we can have +0 and -0 even, and that those are 2 different encodings because of the way that these are designed. And then let's take a look at our case 3, our special values, which are the values that typically are kind of mostly going to be meaningless for us in most of our computations. So when our exponent field is all ones, then that can represent one of 2 outcomes. Either it's an infinity value, and so it's an infinity value if my entire fractional field is all zeros, and I can get that. I get that kind of result if, say, for instance, I take a value and like divide it by 0, I get infinity that way. Or if I took -1 as well and divide it by -0, or a number of ways. You probably think of many ways that results in mathematically a infinite sequence. This is going to be the representation of that. This is how your system knows, oh, you've hit an infinite value. The other case, though, is not a number. Not a number would be encoded as our exponent field being all ones, and then our fractional field being all zeros. And so this can occur, like if you take the square root of -1, right? That normally resolves into a complex number. Or if you try to take 0 and multiply it by an infinite number, that would also create a not a number. Okay. Anyway, so those are all the cases by which our floating point numbers can be realized. So you could see the normalized case is probably what you're going to see most often. Your zeros, your very small numbers, are your denormalized case, and then your case 3 is just like infinity. So if I want to visualize that, this is how it would look like. At my center, I actually have a -0 and a +0, but most systems will have those so that they treat those in a similar way. And then I have my denormalized cases that are close to 0. And then as I step further and further in magnitudes from 0, I get to my normalized cases until I get to my infinite encodings and finally my not a number encodings. Okay. Let's look at more examples. We looked at the one example, but let's take and we'll look at examples that aren't 32-bit. I want to illustrate that this encoding works for an arbitrary number of bits, right? And so we'll look at like 6-bit and 8-bit sequences just to see how the math falls into place. So some common properties based off of a k-bit exponent and an n-bit fraction is that our 0 value will always be represented by a binary string of all zeros. That's going to be pretty consistent. Our smallest positive denormalized value is going to be based on our bit representation has to include a 1 in the least significant bit. And so our values then can be defined in terms of this formula. I don't want to spend too much time just looking at the formulas. I'm going to plug these terms into the formula when we actually look at the examples. I'm just illustrating that our mathematical formula is on the slide. So if you want to go and use this as a reference point, you can look at the actual hard numbers we're going to look at to see where they came from. My largest denormalized value would come from this formula. My smallest positive normalized value comes from this formula here. My 1 is going to be represented when my least significant bit of the exponent is equal to 1 and all the other bits are 0. My mantissa is 1 and my e is equal to 0, right? My exponent value is equal to 0. And then my largest normalized value is going to be when my sign bit is 0, my least significant exponent bit is 0, and all the other bits are 1. So, which again can be represented in this mathematical formula. So I give a kind of a descriptor here as well as our math. But now let's actually go and step through and actually do some evaluation. So imagine we have this much smaller representation where my fraction field is only 3 bits, my exponent field is 4 bits, and my sign bit is 1 bit. Now notice, since I illustrated that we can have k number of bits and n number of bits, I get to define how big each of my fields are. Now, normally in the representations we saw before, we had our exponent field smaller than our fractional field. But for this example, it doesn't have to be the case, right? Okay, so all the more reason why a particular standard is used, though, right? It's like one thing to have a math formula. It's another to say this amount of bits is allocated for one part of the field versus this amount of bits allocated towards another field, because these all generalize out. Okay, so in this instance, this is an 8-bit floating point representation. This is my sign bit, the most significant bit. The next 4 bits are going to be my exponent, which would then have a bias term. And so based off of how we said we compute the bias, our bias is going to be 7, right? Because that's going to be 2 to the power of 3 minus 1 for 4 bits on our exponent, right? So whatever term we would have for our e term, we would then add 7 to it, right? And then I would have 3 bits for my fractional field. And then bias. And then if I were to compute that, I can then see that our for our denormalized numbers, so those are the ones that are approach 0, right? Those are the ones that are as close to 0 as possible. I can get as precise as 1 to the power of 64. And how do I get that? Because remember, the denominator is based off of our is going to be based off of the number of bits that we have to encode our e term for. The 2 to the power of e. So in this instance, we'll be able to go ahead and do 64, 1 over 64, number of ranges. Actually, should be 512. Let's see. Yeah, because we can encode numbers again into our fractional domain as well. So if we go and plug, we can see we get all the way to 2 to the power of minus 6. Because of our bias term that it allows us to shift left or right as well. So our normalized range is going to be a positive anywhere between 1 to the power 64 to 15 over 512, which is going to be our larger numbered range that we can get into. Let's actually look at actual numbers. So if I wanted to go ahead and have this is still my 8-bit representations. What we see here is my binary string, right? So my sign bit, my exponent field, my fractional field. So this is my e term, and this is going to be my value. So this is going to be my largest denominator, my denormalized value, which then leads to my smallest normalized value, right? That makes sense. As you grow out of your denormalized value, because those are the ones that are close to 0, you'll eventually turn into a normalized value, which is actually going to be a bigger term. And again, that all depends on what gets encoded in my exponent field on whether it's considered normalized or denormalized value. So there is a breaking point between those two, where you transition from being a denormalized number to a normalized number. Actually, let me get to, so that this isn't so, again, I have an example for a 6-bit representations as well, but I want to stop looking at just numbers and I want to look at this graph for a moment, because I keep talking about normalized and denormalized, but I want a visualization so that this isn't just an abstract concept that you're having to imagine. So here, my denormalized values are in these diamonds right here. So you can see very compressed to 0. And you could see the amount of encoded values for my, in terms of magnitude, in my normalized set of values in this instance is going to be minus 15 to 15 or close to that, right? It looks like it's actually going to be minus 14 and positive 14 is going to be my normalized value. And then approaching 0 is where it then becomes denormalized. And then finally, my infinity values are going to be when I fall outside of my encodable range, right? So for me, infinity is if I get to 15 or if I get to minus 15. Notice those are highlighted in yellow because I can't encode that. I can't encode that magnitude given just a 6-bit format. That becomes uncountable for me. It becomes equivalent to infinity. So let's zoom in on that. We can see my denormalized space would populate anywhere around here, 0, and all the values by which my exponent field is all zeros, but my fractional field is not. And then at one point, as soon as I have to add a non-zero term into my exponent field, I then become a normalized value. But I'm still could be close to 0, but not as close as the denormalized numbers. And again, I can actually look at all these just by looking at the sequence. I can then plug those into the formula and easily ascertain what is my E value in both my bit or binary encoding and in my mathematical formula, right? There's a one-to-one correspondence there. So this is just an example where you can translate these into the actual decimal representations and the fractional representations into the individual values that form that mathematical expression. So if for any reason you wanted to really get a strong handle on this, I recommend looking at, kind of examining this slide in more detail. This is one of those concepts that it's nice to know, but you almost never actually use it in the real world. Because it's an elegant solution that's implemented for you, and you rarely have to touch it. But it gives you a deeper understanding on how things can go wrong with your floating point numbers. Okay, let's talk about rounding in our floating point arithmetic, because that's a big and powerful concept, right? Because unlike with integers, we don't really, everything's an approximation. So our rounding basics here, we're going to represent our real arithmetic approximations with an aim to finding the closest representative value of x prime to a given value of x. So there's a couple of different ways we can round. You've probably learned how to round in childhood, right? Like in one of your remedial math classes. So there's 4 basic modes of rounding that you should be aware of. And then we'll talk about the one that actually gets used inside of C, so you're aware. You have round to even. So round to even rounds to the closest even number. You have round towards 0. This rounds positive numbers down, net numbers up. So you're rounding towards the direction of where your 0 is on your axis. You have rounding down. This doesn't matter if it's positive or negative. You just round the number down. Or you have rounding up. Doesn't matter if it's positive or negative. You just round it up. So a quick look at what this might look like. Round to even. This is where you're rounding to the next closest even. The closest even, if let's use dollars, because that's a good approach. That's what the book uses. So let's suppose you have $1.40. If you're going to round to even, you're just going to round that down to 1. Or If it's 1.6, we'll round it to 2. If it's 1.5, you're going to round it to 2. If it's 2.5, you're going to round it to 2 as opposed to 3. And if it's minus 1.5, you'll round it to minus 2. If we do round towards 0, clearly we're just rounding it towards the direction of 0. So this, we're rounding off, we're truncating with the one exception, you're truncating here too. And round down, we're just rounding down, and round up, we're rounding up. Pretty obvious in terms of how those concepts work. Okay, so we use round to even for our floating point arithmetic. So, and why? Because it avoids statistical bias in calculations, and it can be applied to both decimal and binary fractional numbers. So some examples of rounding down in binary are given right on that slide. And just some examples of how this might look. Rounding to the nearest 2 to the power of minus 2. Here we have where the rounding occurs inside of the red. Okay, let's talk about our floating point operations. So the operations that we're really going to look at mostly are going to be addition and multiplication, because that's what we looked at with our integer numerical data types, right? And so one thing you should know about how our addition and multiplication works is we do the addition, we do the multiplication, and then we do a round to ensure that whatever the resulting value is then fits within our word size. So, and then the rounding approach we're going to use is the one that we had simulated up here, which is going to be our round to even. Okay, so some quick things you should be aware about, because unlike with integers, where we could rely on our arithmetic operations mimicking that of mathematics that you're familiar with, there are some properties that are not guaranteed with our floating point operations, and we're going to look at that. So, but first, let's define some definitions so we can articulate how this is different. So, is everyone familiar with the Albion group properties for arithmetic operations? So, what it means to be commutative and associative, and to be monotonic, and for a set or a value to be closed. So commutative just means that the operation is commutative if changing the order of the operands does not change the result. The operands are the values. So like 4 plus 3 is the same as saying 3 plus 4, right? So it's associative if you have an operation where you have groups of operands. So you can have more than one operand, and you can change the order in which you do your operations. So this is like saying like 1 plus 2 plus 3 is the same as, you know, putting the parentheses and moving the parentheses. So you could do one set, you can process one set of operands in any order and it still produces the same result. If that's the case, it's associative. So monotonic simply means it's one of these, and let's look at the example for this. So it's a function or operation if the output is consistently increasing or decreasing as the input consistently increases or decreases. So if my input's increasing, then my output's also going to increase. If my input value is decreasing, then my output value would be decreasing, right? So if you think of addition or multiplication, you could see how those are typically monotonic functions or operations. And then finally, closed just means that the result of the operations between two elements is always results in something in the same set. Okay. So one of the first things that you have to do if you're going to do addition with our floating point numbers is you have to have your binary point aligned. right? You can't do addition with misaligned binary points. So once you have them aligned, and I don't think I actually have an example, then you can do addition the way you would normally do, like you do like long addition, but in order to find your V value. But the things you should know about this is we do have, it is closed under addition. It is commutative, but it is not going to be associative. And so what that means is our overflow and exactness of rounding means we can have these two same set of terms, but depending on which operations we perform, and this is with addition, we could either get a 0 term or 3.14 term. So that is unlike what our integer arithmetic or addition would allow us to do. Okay, and so very similarly, looking at some floating point multiplication. And again, the way that we can kind of see how this works is we can re-express our terms in the formula that we saw to find what our E value is. And then you can go ahead and combine those terms and then just compute your new term. So you can see how multiplication is, it's actually relatively easy to do using our floating point operations. And again, just comparing this to see what behaviors does it have as it does towards integer operations. We could say that is it commutative? Yeah. Is it associative? No. Yeah. All the same concepts, because again, processing these operations can result in an overflow that then, because of the inexactness, can actually produce two different results based off of the order that you actually process your values at. And again, I give examples where you could see we get two different values based off the order you compute these at. Okay, so some comments about how our floating point numbers are implemented in C. We have two levels. We have a float, which is our single precision. We have a double, which is our double precision, so 32-bit versus 64-bit. We can convert by casting operations. So you can cast between ints, floats, and doubles. I'll actually leave it as an experiment for you to see what happens. I think the book actually has some nice puzzles to see what happens when you take a double value and cast it into an int, or a double value and cast it into a float, or a float value and cast it into a double, right? Certainly there are some, just like the concept with anything else, there are some where you get exact conversions, like if I have an int and translate that into a double, or if I have a float and if I translate that into a double, I can have exact representations. And of course, I'm going to have lossy representations where values get truncated. So just keep that in mind. Other than that, yeah, that is all that we have to say about the way that we store data inside of our system. So we are done with storage. We will move on to chapter 3 next lecture. Excellent. And by the end of today, all of the videos for up to chapter 2 should be available on the playlist, which means that it can also go ahead and publish the next labs, which is going to have you play around. It's the data lab. So you'll be able to play around with all these number representations using primitive operations to try to achieve the results that you would do either by hand or with more complex operations, or actually complex operations that would normally be basic operations, but you can't use those operations or those operators. Okay, so other than that, I will see you all on Tuesday.